So in this lecture, we're going to look at heat conduction. The idea is that we're going to do the same procedure, right? Remember that everything that you are learning in these lectures can be applied to elliptical problems, right? So these are simple differential equations. Like we can have other types of differential equations, but the heat conduction is a very nice equation because it nicely helps us transition to higher dimensions, right? Heat conduction is a very nice problem because we are still for instance, in 2D or in 3D, we are still dealing with a scalar field, which is just the temperature field, right? So I find looking at the heat conduction a really nice way to transition our formulation to higher dimensions. And you will see that essentially the difference between a two-dimensional heat conduction problem and a two-dimensional elasticity problem, there are some subtleties here and there, but it's essentially the same thing, right? And so let's get started. So we're going to look at the same thing, and hopefully in one lecture we're going to cover it all, from the strong form to the weak or variational form to the discrete Galerkin projection, okay? Also in higher dimensions. So let's see. Well, let's start our discussion of our differential equation. Again, we are going to look at the balance, the heat balance of just an infinitesimal part of our bar. Again, we're looking at a one-dimensional problem. We start everything from 1D so that whenever we transition to 2D and 3D, we see what are the differences, right? It's essentially the same with some subtleties here and there, but it's essentially the same. So if you recall, well, we're going to use Fourier's law that basically says that the heat flux is the negative of the gradient of my temperature field. So this kappa here is my conductivity of the material, and du dx is the gradient of the temperature. And again, this is just basically simply saying that heat flows from regions of higher temperature to regions of lower temperature. So if I now look at the balance, let's say in a way equilibrium of heat fluxes in that infinitesimal piece of the bar, then I have basically Q, which is my heat flux at x plus delta x multiplied by the area. I have to consider the area of that section, minus Q of A, which is this part here, is going to be equal to F, which is my source term. This is essentially potentially something that is generating heat inside my bar. And so that equilibrium has to hold. And then we do the same thing we did for the one-dimensional elastostatics problem. We divide by A dx, and we take the limit. And so the first term here is essentially the definition of the derivative. So this is going to become dq dx minus f is equal to 0. Now, when we apply, or we basically plug in what the heat flux is, our differential equation becomes very simple and very similar also to my one-dimensional bar, right? If you remember, my bar equation was ddx, and then I have EA. That EA is my axial rigidity. Here it transforms to my conductivity, and then I have the gradient of the displacement. Here's the gradient of the temperature, plus F. In the one-dimensional elastostatics, that was my load per unit length. Here's my heat source, is equal to 0 for all locations along that bar. Again, this is my differential equation, but yet we do not have our entire boundary value problem because we need boundary conditions to do that. Well, it turns out that if I consider no source, right, I can remove this. Is going to be, let's say, equal to 0. Then this goes away, and then I get the so-called Laplace equation. Otherwise, this is called the Poisson equation, right? And again, I love this equation because it helps us learn so much about how to transition from a one-dimensional world to a higher dimensional world in a very simple way. Okay, as I said, in order to set the proper boundary value problem, we need boundary conditions. And so there are how many boundary conditions? How many? No. 3, which are Neumann, Dirichlet, Robin. How many? 3. Okay, so my first boundary condition is my essential boundary condition on the now displacement field. So this is now the primal field. My primal field now becomes the temperature field. It's not the displacement anymore, right? I still use the same symbol because, well, that's what we normally use. I could have also chosen for t uppercase because lowercase t is time, but we understand that when we're talking about u, we're talking always about the primal field. In this case, it's going to be the temperature. So from context, we realize we're talking about the temperature. So we write u in gamma d. Remember, gamma d was the region of my domain with prescribed directly boundary condition equal to some value that I want to prescribe. I can also prescribe the boundary flux, right? And I'm going to do it like this. I'm going to say minus q dotted with n is equal to q bar. So this is going to be my prescribed boundary flux. And again, I'm going to look at that n. If you recall, that n was used in elastostatics in 1D for doing what? Recall that? Yeah?
To ensure that the sign convention.
Yeah, it was to ensure our sign convention that negative strain in the bar implied that your bar was under compression and positive strain tension, right? So we're going to do the same thing here, and we're going to analyze what this is going to be in a minute. And now I have my Robin boundary condition that, if you recall, was some sort of mix between these two boundary conditions, because let's say as I increase that value of h, that in the one-dimensional bar elastostatics problem, this was my coefficient, right? It was a spring, and if you remember, whenever I make that very, very, very high, right, then I was kind of prescribing some sort of directly boundary condition. Well, kind of the same thing happens here.
Choose a negative value of q in the Robin and the Neumann boundary condition so that your derivative is positive.
We will look at that in a second. We will get there. So now, in this particular Robin boundary condition, h is the so-called heat transfer coefficient, and normally u infinity is your ambient temperature. So this is a very known boundary condition for heat problems called the convective boundary condition. So let's look at that, that convention that we're going to use now, right? And this is going to address your question. So now the convention for n, right, ensures that heat flux is positive when heat enters the bar and negative otherwise. So if I look, for instance, at a point like this, right, basically I'm going to choose the value of n so that the heat flows in that direction, right? Again, ensuring that given Fourier's law, heat transfer for regions of hot temperature to lower temperature, and so red here is like hot, this is cold, right? And so heat is going to be flowing like that. And if I look at point 1, you can see this whole expression here, right? This whole thing here is minus q, and so I'm going to have to choose n is equal to minus 1, similarly to the case of the one-dimensional elastostatics bar, in order to have, let's say, a positive prescribed boundary flux, right? And obviously, because the heat travels in that direction, if I look at this point here, well, heat is leaving the bar, and therefore I have that expression here that basically says that my prescribed boundary heat flux is going to be lower than 0. So it's just a simple convention. We do the same here for the other case where my gradient now is positive. Here my gradient is negative, but it's essentially the same thing. And so we are choosing that value of n to ensure that we comply with our convention. That, again, heat enters the bar when the heat flux is positive. Okay? All right, now we are ready to set our boundary value problem, right? Now we have our differential equation, we have our boundary conditions. And so similarly to our one-dimensional bar, we have two ends in the bar. And so we have to pick and choose, either two sets. Either we have a Dirichlet boundary condition at the end, right? Or we have a Newman boundary condition at the other end. Or we have a Dirichlet and we have a Robin. Or we have a Newman and we have a Robin. Or we have two Dirichlet boundary conditions, in which case our boundary value problem is a pure Dirichlet. Or we have two Newman boundary conditions, in which our problem is a pure Newman problem. And can we solve a pure Newman problem?
No.
Yes, we can. We can solve a pure Newman problem, okay? It's just singular. So how many solutions you have in a singular system?
Yeah.
Infinite. Can I pick any solution? Yes. And so again, you're going to solve the problem up to a constant. I just not going to know a specific temperature, but if I'm interested in the gradient, I can still solve the problem. You have a question?
But what if you put in 2 watts on one side and 0 watts out the other? Then it's just infinitely going to heat up.
It's a pure Newman problem. You have an infinite number of solutions, right? Infinite. But if you're interested in the gradient, because if you want this a gradient, it's the same. Think about the elasticity problem, right? If I say I'm going to prescribe a force here, right?
Yeah.
And then I'm going to prescribe a force there, you can still solve the problem. It's just that it's going to give you an infinite number of solutions. Obviously, those forces have to be self-equilibrating ones, right? And so that is the caveat to it, okay? All right. Recall that solving the strong form, and this is a very important, this is the motivation why we need a different formulation, right? Solving for the strong form, that is to say, satisfying the equilibrium equation for every x along the bar and the boundary conditions may not be straightforward. And again, for the one-dimensional case, it's super straightforward, right? We can have our differential equation, integrate twice, get the constants of integration, applying boundary conditions, and we solve our strong form. Yeah, okay, in 1D. 2D, it's impossible. Unless you have some nice geometry, you take advantage of symmetries, you simplify the problem in a way that you can actually form the, you obtain the solution of the strong form. Now, what do? Well, we go for a variational form or a weak form of equilibrium, in this case, heat balance. And so we take our differential equation, we multiply it by a test function, we integrate over that domain, and we say that that has to hold for all test functions in a given space. Same thing we did for the one-dimensional bar, nothing changes. And then we do integration by parts. Who remembers why we did integration by parts? Yeah?
To relax the condition.
Yeah.
How do you put it? The sheet condition. How do you put the differentiability?
Exactly. We do integration by parts to relax the differentiability condition on U, because here you have to apply a second order derivative. But here, once we do integration by parts, we get that term. And now we get a symmetry condition as well. So we not only lower the differentiability requirement on U, right? So now we can use, for instance, linear polynomials as a way to approximate the temperature. Before we couldn't. Now we can. But we also make this symmetric. And that, again, is important because it leads to some really nice properties. It leads to a symmetric bilinear form. And a symmetric bilinear form leads to a symmetric stiffness matrix. In this case, we're going to call it characteristic matrix, right? It's no longer a stiffness matrix per se. It's something else. But it's going to lead to some nice properties. And while we do the integration by parts, we get this term here that is what? Huh? Yeah, so the natural boundary conditions arise naturally in the formulation. And if you can see here, the moment I basically expand this term, and I basically just, I do this term at L minus this term at 0, right? And then I change that minus to a plus, but then I put that minus here. Then you could argue that this guy is N, this guy is N, and so my boundary conditions arise naturally in the formulation by just performing integration by parts. So then I can write this whole expression simply like this, where I have my boundary flux boundary conditions, and then I have this term that is going to be part of the so-called bilinear form. Yeah.
In the elastic beam problem, the boundary condition part becomes basically the actual stiffness, and so like you can cancel it out.
Yeah.
Is it analogous here?
Yeah, it's exactly the same. And again, it's very similar because the differential equation that we're looking at is very similar, right? Again, we did this comparison where you could say, well, in this case, U is the temperature. In the elasticity, this is the displacement. But this K, this kappa is my conductivity. In the elasticity was my axial rigidity, EA. And then this guy here is now the heat source term, whereas in the elasticity is my load per unit length. And again, just because the equations look the same, we're going to get to the same type of outcome when we obtain the variational form. And so, yeah, again, the natural boundary conditions emerge naturally in the formulation. And then we are ready to set the variational form, which is basically, well, now we're interested in finding the temperature field U in some space, right? We're going to talk a little bit about that, such that the bilinear form is equal to the linear form for all test functions in that space, where for this particular problem, right, my bilinear form has this shape and my linear form has that shape. Now, you see that I'm still able to represent this problem in abstract form. And again, this is always the case. You can always represent your variational form this way. It's just that the shapes of those bilinear and linear forms are going to change depending on the problem that you're solving. You had a question back there?
Yeah, my question was on the term W0, Q bar 0, why is the sign positive and not negative?
This one? Oh, this one.
Yeah.
Yeah, well, we saw it here. Here, right? So what I did, if you notice, is that I replaced all of this, right? And I evaluated on the right-hand side, right? Minus this whole thing evaluated on the left-hand side. So that minus is basically here, but I put a plus here. And then I say, well, this is going to be my n. Just to fulfill the convention that I want that boundary flux term to be positive whenever heat is entering the bar.
So
Yeah?
it's implied inside of Q bar.
Okay. So let's look at an example to derive the weak formulation. And well, we derive the weak formulation here, but just to make it more interesting, let's assume that now I'm prescribing a convective type of boundary condition at one end. So I say, well, I have my bar, and I want to set the temperature to U bar, not to 0, but to U bar. So basically, I cannot find U in V naught, because if you remember, V naught had to be satisfied equal to 0 at the Dirichlet boundary condition, so I'm not interested in that case anymore, right? I have a U bar, and we did a little trick for the elasticity case. If you recall, we defined this so-called linear variety, which was a translation of a space by a constant function that satisfied the Dirichlet boundary condition. Right? We're going to apply the same trick here. So, but on the right-hand side, we have this convective boundary term. So remember, this is the heat transfer coefficient, this is your ambient temperature, and this is the yet unknown temperature. Remember that the Robin boundary condition has two parts. One part that you know, that is eventually going to sit in the part that you know sits on the force, or on your right-hand side of the equation. The part that you don't know sits on the bilinear form, or your left-hand side of the expression. You guys are getting it. That's it. There is no more to it. You get this, that's it. You get the course. Okay, so again, we're going to do this. We're going to take our differential equation, multiply by a test function. Remember, these are our projection. This is our projection statement. These are, again, to me, the best invention in mechanics. The projection is like crazy. Remember, we're going from infinite dimensions to a finite dimension. Not yet, this is still infinite dimensional, right? But this projection is crazy, saying that my differential equation has to be orthogonal in the sense of the bilinear form, right? To my test function is insane. These orthogonality conditions is, again, a really great invention. Well, when you do integration by parts, right? Recall that the boundary terms show up, but I am prescribing the Dirichlet boundary condition at one end, right? That means that I have basically a reactive flux on the left, right? But why this goes away? Yeah?
The test function, the weight function.
Yes, we choose a weight function to belong to that V naught space, and so my test function is going to be equal to 0 at that location. That's why this is going away, and I don't have to deal anymore with the reactive flux. Okay, and then then I have to deal with this boundary term here. But on the right, this guy is that guy here, right? And so when we replace that, we have our convective boundary condition, and as you just said, that is going to have a part that you know, which is this guy, and a part that you don't know, which is that guy, right? And so when you set the whole problem, the idea is now we're going to transform the abstract form. We're going to express my function u as the sum of two functions, right? One that is satisfying the Dirichlet boundary condition that I want to prescribe, and one that is not known yet, but which belongs to that space V naught. Remember, this is just a little trick that we applied, right? We say, I am going to express my function u as the sum of two components. One V that I do not know, and one u tilde that prescribe the Dirichlet boundary condition, right? But I'm going to choose this V in the same space from the test functions. And now I get all these nice properties back. I do the Bubnov-Galerkin approach where my test functions and my trial solution eventually are going to be chosen from the same space. I get symmetry, and again, the same story. Symmetry leads to nice properties, symmetric stiffness matrix, less number of operations if I want to solve with a direct solver, with Cholesky factorization, like all these things. And so I restate the problem where I now say that I have to find my V in this V naught. V, again, is going to be equal to u minus u tilde, such that my bilinear form is equal to the linear form minus this term here. Again, it shows up in my right-hand side because the known displacement, in this case temperature, is going to change my right-hand side, right? And then that has to be satisfied for all test functions in V naught. And again, because I'm now dealing with a convective boundary condition, in addition to these terms that we looked earlier, then I get these other two terms here that show up simply because I have a convective boundary condition term. Okay?
Also that because you chose u tilde you imposed that, how do you say that u tilde is a Dirichlet boundary condition, that we also choose then a test function again so that one becomes 0, so that you only end up with the V part of u minus u tilde.
Yes, yes. So if you look at this, so if I write u is equal to V and u tilde, well, obviously, since this guy here satisfy the Dirichlet boundary condition, obviously that guy here has to be equal to 0 at that location. Yeah? All right. Let's move to higher dimensions because this is where the fun starts. Everything that we have done so far is like, okay, kind of replication from what we have done. Yeah? So let's move to higher dimensions because this is where things are going to get more interesting. Good news is that most of the things that we learn are going to apply the same in higher dimensions. And you will notice that here and there's a slight difference, but overall, it's exactly the same thing, okay? Before we get there, let's recall what a divergence is and what the gradient is. Okay, so these are operations that we define them to be this way. So the divergence of a tensor, of a vector V, right? So here S is going to be a scalar, V is going to be an n-dimensional vector, and T is going to be an n by n, let's say, a two-dimensional tensor, okay? To make things simpler, we're going to define the divergence of a vector as dvixi. So remember that the divergence reduces the rank of a tensor. So if I have a vector here, the divergence is going to reduce, that rank is going to become a scalar. So if I have the divergence of a tensor, which is a second order tensor, it's going to reduce the rank of that and it's going to become a vector, right? So this operation here, the divergence of a tensor, is, well, the derivative of Tij with respect to xj ei, right? Now, yeah. So there are different conventions. This is one of them, right? Some people write the divergence of a tensor differently, so they swap these indices here, right? But this is the notation that we're going to use for the course. Again, it's just a matter of convention, and as long as you follow your convention everywhere and you remain consistent, that is totally fine. Okay, now the gradient of a tensor, the gradient operator is going to increase the rank of a tensor, right? So if I apply that to a scalar, this is going to become a vector. If you apply that to a vector, it's going to become a tensor. So these are basically just a reminder. All of you at this stage should know this. And so let's see how we can get now our problem now that we recall these operations. We're going to start again with the strong form. So now I'm going to have my d-dimensional body, let's say 2D or 3D, right? And then, of course, that's going to be a part of my d-dimensional space. I'm going to define a normal over the boundary. My boundary is still going to be called gamma, right? And then that's going to have a normal field. So at every point along the boundary, I can just plot a vector of unit magnitude that is the normal to the boundary, right? It's going to be a field. And again, this is going to be subjected to different types of boundary conditions. So I'm going to have the same 3 boundary conditions, Dirichlet, Newman, and Robin boundary conditions. So the strong form is going to be pretty much the same, given the thermal conductivity kappa, and now kappa is no longer going to be a scalar like in the one-dimensional case, but you could assume that you have different conductivities depending on the direction, right? You can say, well, maybe my 1 component of my kappa tensor, so this kappa is basically a d times d dimensional tensor, right? You could argue, well, maybe I want my conductivity in the x direction to be different than my conductivity in the y direction, and it's totally plausible to have something like this, for instance, with you have laminates or this type of materials, right? I'm going to have a heat source, right? Prescribed temperature, again, part of the domain I want to prescribe a temperature, and then have my prescribed boundary heat flux. And so the objective is going to find the temperature field again, which is a scalar field, and that's what I like about this problem, because we are moving to higher dimensions, and our domain is going to be higher dimensional, but our field remains scalar. That's why this transition is so nice before we get to the full elastodynamics problem. Sorry, elastostatics problem. No dynamics in this course. And so now my differential equation is going to be looking like that. And obviously you can get to the same equation by doing the same thing we did in 3D. I'm not going to go through that because it just takes time and it's the same and the same and the same. But you can take an infinitesimal cube of a 3-dimensional body, and let's say what is the heat balance in the heat that is going in the x direction, and you do the same thing we did in the 1-dimensional case. Well, now you get d equations, d depending on the dimensionality of the problem, and then essentially you can write that equation like this, right? So the divergence of kappa operating on grad u, the gradient of u, right, plus f is equal to 0. Notice that it's still a scalar field, so on the right-hand side I have a scalar. So what do we have on the left-hand side? Well, grad u is what? It's a vector. Now, if I have kappa, which is a 2-dimensional or a second-order rank tensor multiplied by a vector, that gives me a vector. And if I take the divergence of a vector, I get a scalar. So a scalar plus a scalar is equal to scalar, and we are in good shape. All right, boundary conditions, same thing as before. We have 3 kinds. We have u equal to u bar, which is a Dirichlet boundary condition. We now have this expression here, which is looking strikingly similar as the one that we did in 1D, is that now we're using basically this dot product to get a scalar, right? So grad u, basically, this is a vector, kappa grad u is a vector. Now we have the direction, so we do the dot product, and now we see what is essentially the heat flux in the normal direction. That is going to be equal to my q bar. And the same with the Robin boundary condition. So this is a strong boundary value problem. We still have 20 minutes. Yeah, so we're gonna manage. So what do? We are not happy with that statement of equilibrium, right? Because again, finding the exact solution is extremely hard in higher dimensions. And so we state a different form of equilibrium. This is going to be on average. Notice that I am multiplying again by my test function, my weight function, integrated over my entire domain, that now is a 2-dimensional or 3-dimensional domain, and setting that, oh, I forgot here, this is supposed to be equal to 0. Yeah? So that's something I have to fix for all test functions in some space. Again, we note, we always make sure that our test functions are going to be equal to 0, where the Dirichlet boundary condition is, simply just because we don't want to deal with the reaction term, right? Otherwise, we have to do something extra in order to solve the problem, right? But I just get away by not dealing with the reaction at all. Same thing as before. Also notice that I'm still making some sort of product between 2 scalars here. And this is going to be different when we move to the higher dimensional problem in elastostatics, because then we are going to be dealing with vector valued functions, right? Every vector, every component of a 2-dimensional vector is going to be a function. So it's different. Here, we're still still dealing with a scalar field. All right? That's why I take my scalar differential equation, multiply by a scalar function, integrate over that domain equal to 0 for all test functions. Okay, and then what do we do? Same process. Integration by parts, not yet. We will see that in a minute. We're going to apply this identity, right? The identity is if you take, so I want to basically balance the term of that guy here. And so we're going to apply these identities that says basically that that term is equal to this term plus that term. And well, just so that you don't have to believe me, I put here at the bottom the derivation of why that is. Not much to it, but that identity holds, right? And you could argue that it's some sort of way to balance the derivatives, which is what I want to achieve in the end, right? And so when I replace that term by this whole thing, right? I put it back, then I get this whole expression right there. And now we have to move forward with that expression. Now I have achieved one thing. I have balanced the derivative, the differentiability requirements on u and the test function. They are the same. So again, this term is going to be part of my bilinear form. Very good. Now I have to deal with that term. So what is that term? I have, some sort of the divergence of all that expression there. I would actually have to put this guy here, right? To make it really clear. I have another problem to fix there. Let's try to figure that out, right? So we're going to use now the so-called divergence theorem or Gauss theorem, right? The idea here is that I want to transform this entire integral, right? The divergence theory allows you to transform an integral over your domain in an integral that deals only with the boundary, right? That is the essence of the divergence theorem. It's really a great mathematical tool that allows us to actually get our boundary conditions. They emerge naturally in the formulation. So again, transforming that integral over the volume to that integral over the boundary, I see that basically I get that term that is essentially my Newman boundary condition right there, right? So how does the divergence theorem work? Well, I take whatever the divergence is acting on, right? This thing here, and I basically do the scalar product with the normal to that, and then that's essentially my, it is defined like this. So these two quantities are equal. So now I get these terms here. Those are my boundary conditions. And obviously, I have to write this whole expression. Remember that this whole expression is over the entire boundary, right? The whole boundary. But again, as we know, my boundary is going to be comprised of the Robin boundary and the Dirichlet boundary and the Newman boundary. These are, of course, mutually exclusive. They are not overlapping, right? They are disjoint, right? So I could write this whole thing in a sum of 3 boundaries. So why you see only 2? The other one is 0. Why?
Because we choose the test function.
Thank you so much. We choose the test function so that is equal to 0 in the Dirichlet boundary, so we don't have to deal with that. And because I didn't have enough space in this page to put it, so I didn't put it because of that. But you already know this. You are getting the contents of this course. You are becoming experts of finite element analysis as we speak.
I have a question about that, because what you define actually, if you look at the second term of the divergence, is a flux. And a flux doesn't really make sense in a Dirichlet boundary condition, right? Because
Well, you have your reactive flux.
oh, I see. Okay.
Yeah. Okay. So now we're playing the same trick. If there is a part of the boundary where we want to prescribe the Dirichlet boundary condition, right? Like a non-zero Dirichlet boundary condition, we form our linear variety, right? And if you recall, a linear variety, we call it V star, is essentially a translation. So this notation makes no sense, right? Because you are basically adding a space to a function. So it's conceptually, the way you have to read this is that I'm basically taking that space and I'm translating every function of that space with this u tilde that satisfies a priori the Dirichlet boundary condition, right? So u tilde is satisfying my Dirichlet boundary condition, right? So we apply that trick, and then the weak form becomes, well, given u tilde, find V, which is the unknown part of my temperature field that is going to be found in this V naught, such that my bilinear form on V, right, is equal to my linear form minus the term that again is going to modify the right hand side, because this part is something that I know for all test functions in my V naught, right? And again, now I wrote, if you read that statement here, right, this applies to every problem we have seen so far. But now, because we're dealing with higher dimensional heat conduction, now the concrete shapes of the bilinear and linear forms are given by these two terms, right? Where you see that indeed we're dealing with higher dimensional heat conduction. Yeah. So far so good. You see that very nicely we move to higher dimensions. It was pretty much the same, except for a couple of things. It was essentially the same, right? The only differences, as you saw, is that, well, now we are dealing with tensors, we're dealing with vectors, and then we had to use the divergence theorem to transform that integral into a boundary integral, the domain integral to a boundary integral, so that our natural boundary conditions pop up in the formulation. But other than that, it's exactly the same procedure, right? Okay.
Our end statement is just a scalar statement. So
Sorry?
our end statement is just in a scalar form.
Yeah, it's a scalar form. So that it's still going to be the case in higher dimensional elasticity. We're still going to have a scalar statement of equilibrium. But we're going to get there later. All right, so remember that this is still living in an infinite dimensional space, right? So again, it is an equivalent statement of strong form equilibrium, right? Why? Simply because, well, in this form, we can still supposedly get the exact solution of the problem, right? Now, we don't want that. We want to crunch numbers in a computer, so we reduce the dimensionality of our problem. And so we're going to take V not H. H, remember that we use a superscript H to denote that we are now living in a finite dimensional space. That is, of course, a subspace of my infinite dimensional space, obviously. And then my statement of equilibrium is going to be similarly as before, but everywhere where I had a V, I'm going to have a VH. Everywhere where I had a W, I'm going to have a WH. And that's it, right? And of course, I'm going to pick these guys using finite element spaces. And yeah, so things are going to get interesting when we look at finite element spaces in higher dimensions as well. So looking at the eth element, right? Now I can obtain, I want to obtain the global equilibrium equations, the discrete equilibrium equations, the same way we did it earlier for the one-dimensional bar. So if I look at the eth element, so I can write the shape functions the same way like this. So let's assume that we're dealing with two-dimensional triangles, which I would argue is the simplest two-dimensional element, the linear triangle. And so this shape function vector, again, is a row vector. What is the size of that vector? It's 1 by 3. Triangle has 3 nodes. Yeah, so it's a 1 by 3, and this is my local temperature vector that is size. What is the size of that? 3 by 1. So I have a 1 by 3 multiplied by 3 by 1. I get a 1 by 1. It's like I get my scalar field inside the triangle, right? I represent the test functions the same way. My weight function is the same way. I represent the trial solution, right? And so when I look at the element heat balance, right, I get my local stiffness matrix. It's not a stiffness matrix. Remember that we're going to call this a characteristic matrix for my heat conduction problem. I don't know exactly how this is properly called in heat conduction. I never managed to find that, so we call it the characteristic matrix because it's not stiffness anymore. And then I have my local force vector, right? And so now the difference is that there is going to be these matrices B, right? that essentially I have to apply the derivative, so the derivative of each one of these shake functions. And in 2D and in 3D, that differential operator simply looks like this, right? Now, in elasticity, this is going to be different, and we're going to get to that in the next lecture. But for the heat conduction problem, this is just very straightforward. And so this is my local equilibrium, right? Because essentially, then I can get to my Ke multiplied by U equals to F, and that is going to be my local heat balance, right? So obviously you get into the same Ku equals F system of equations, and we managed to get through the heat conduction in time. Do you guys have any questions? Yeah?
When you change the boundary condition that is formulated in the 3D case when you do a weak form,
Yeah?
I don't exactly know why you just put it in the standard version of each boundary condition. So Robin and Galerkin.
Yeah, yeah.
Because they had a specific, was like a gradient divergence or something, and then you just, it's way back.
Way back.
Yeah.
This term we can,
Back.
in this slide?
No, back.
Back.
Back. Yeah, so you have a boundary condition,
Yeah.
which is x times gradient u.
This term.
Yeah.
Yeah.
I don't get why it's just split into, I get why you split it into the different.
Yeah. So if you notice that the divergence theorem transform an integral over the entire domain to an integral over the entire boundary, but it's the entire boundary, right? And my boundary again is split in different parts. You have the Newman part of the boundary, you have the Robin part of the boundary, and well, I could again write here my Dirichlet part of the boundary. That is going to be something like, let's say like this, right? But again, this term goes away simply because I choose those test functions to be 0 there. Yeah?
No, yeah, I get that, but the boundary condition has terms like u and x, but when you put it in the standard normal condition, the boundary condition and the Robin condition, those kind of go away. Like you're just using the standard definition of the Robin, the boundary condition. But
Yeah, this is
it's
just,
only applied to the problem.
so this guy here, look at it. It's kappa grad u dotted with n, right? If you go back to the way we set up the strong form, it's kappa grad u dotted with n. So it's this term. So this makes it more clear, right?
Yeah, that makes it work.
Because this part indeed is q bar is on gamma n, and this part here is on gamma r. Yeah?
Yeah, thank you.
Perfect. Okay, guys. Any other questions? So then, you have a question? Yeah.
So earlier you said that the test functions need to be in C1, but a hat function is not differentiable at the corners.
Yes, that is true. A hat function is a Z0 function. So we're going to get into a huge, lengthy discussion into why we're looking at functions in C1, whereas in the end we look at functions in Z0 for our finite element discretization. When we talk about C1 and C2, we are still talking in an infinite dimensional space. Okay? So the fact that whenever we move to a finite dimensional space and we choose finite elements, that changes, right? These functions are no longer in C1. So our discretization in the end is Z0. That is true. So your question is, why is that it?
Yeah, why is this allowed? And the answer is, will be explained later.
Yeah, well, it is allowed because in the end, the final field that you get, it's still a continuous field. And you are interested in a continuous field. Not so much in the gradient. So if you require the gradient to be continuous, then yeah, you can even go further and make sure that you use C1 functions, which is, for instance, what happens when you solve for beams, right? In the beams, we have a fourth order differential equation, right? If you just take Bernoulli-Euler theory, the differential equation is fourth order. Then when you balance the differentiability requirements, you get into a second order derivative, right, on the trial solution. And now you need to ensure that you have C1 continuity, otherwise you are dealing with a broken beam, right? So you require not only the transfer displacement of the beam to be continuous, but you also want the rotation of the beam to be continuous, right? Okay, guys, we stop here. In the next lecture, we're going to look at higher dimensional elasticity, and then we're going to look at finally the isoparametric formulation.